All right, so what questions you guys have about the exam format and material? So for people who recently arrived, just waiting for any questions. Okay, maybe we can scroll down the list and see if it elicits any questions, but feel free to jump in with questions about things that I'm not highlighting on the list. So again, this is a comprehensive exam. Definitely will be questions on material that we covered prior to exam 1 and prior to exam 2. So this list that I'm about to go through is the topics that we've covered since then, but you should feel free to ask questions about anything we've covered in the class. So, so just shout out if you have a question. Momentum, impulse. Yeah, go ahead.
Can you talk about impulse? I'm still like a little confused.
Sure. So the general law of the conservation of momentum is that the total momentum of a system initial plus the average external force times delta t is the total momentum final. And so this is the impulse. Yeah, so that's the main answer to your question. We can also use the idea of impulse, for example, to solve for the average external force if we know what the change in momentum is and if we know what the time of interaction is. But more often we're using it to determine a change in the momentum of the system. This is related to a question that came up in the first review session, which is how do you know what to choose as your system when you're using conservation of momentum? And the basic answer to that is don't include the Earth when you're talking about conservation of momentum or anything fixed to it. In your system for conservation of momentum. Now, when you're talking about conservation of energy, you usually do want to include the Earth because you want to be able to deal with gravity using potential energy instead of work. So an example would be the collision of the two cars that were colliding at right angles. There, you wanted to include the two cars as part of your system, but not the Earth. And in that case, we ignored the force of friction. And the reason that we were justified in doing that is that the force of friction, if friction is much less than the force that the cars exert on each other. So because of that, we could ignore the impulse caused by friction during that short time delta t. So partly because the force of friction is small, and partly this is small for the collision itself. After the collision, the force of friction acts over a longer time and brings the two cars to rest during the skid. And during that time, the impulse from friction is not negligible. But during the collision itself, delta t is small, the force is small compared to other forces that are being exerted, so we ignore it. In contrast, when we have the problem of the smart car smashing into the brick wall, there I would encourage you to think of the brick wall as outside the system, but there's an average force that's external that's not at all negligible because it's the main force that's acting on the smart car during the collision.
Wait, so the brick wall wouldn't be a part of the system?
I would encourage you in that case to define the system to be only the smart car and have the brick wall be something that's outside the system. The reason not to include the Earth in your system is because it's hard usually to quantify the changes in momentum of the Earth because it's so large.
Professor, are there situations where we can consider impulse to just be change in momentum?
Yes, absolutely. So that's another way to think about it, is that the impulse is a change in momentum. So similar rule of thumb for when you're talking about angular momentum, I didn't get that far down on the list, but in that case, you also don't want to include anything that is fixed that can't rotate as part of your system. Don't include anything that's fixed and can't rotate. So an example there would be this problem where you had the putty that was falling and was going to hit this little protrusion from this wheel. So there you want to include the putty and the wheel in your system, but not the Earth, which the wheel is attached to. In that case, there was a force being exerted down by the putty on the wheel, and yet we know the wheel doesn't move. And so there was also a force being exerted upward on it to cancel that out so that there's no net force on the wheel to keep it from moving. So that was why in that problem using conservation of momentum wasn't helpful, because this was unknown. You could probably figure it out, but you don't know it. But it exerts no torque because its line of action passes through the axis of rotation. And so that made it easy to apply conservation of angular momentum, but hard to apply conservation of momentum to that problem.
If you're ever doing a problem where you have to use both conservation of momentum and conservation of energy, how does that impact the problem if you're going to basically like use different systems for both parts of the problem, if that makes any sense?
Sure. So there are, I would say there's two classes of problems like that. So one class would be a simple 1D elastic collision. So in that case, let's say, for example, you've got a large object like this that's moving with some velocity like this. It's about to hit some small object like this, and you're just asked to find what are the final velocities. There, the way that you would combine conservation of energy and conservation of momentum is just to use this equation that we derived in class, that the final velocity of either object, let's say this is object 1, this is object 2, the final velocity of object 2 would be twice the velocity of the center of mass minus the initial velocity of object 2. So that's one way in which you might combine it, or have a problem that uses both conservation of energy and conservation of momentum. Another one would be when you are have a problem that consists of a series of things. So we've done several problems where there's kind of a series of different steps. So like this one, in this one, the first step was conservation of energy as the putty falls. Then in this case, conservation of angular momentum during the collision, and then again, conservation of energy for the final rotation. So there, and you might have a similar problem like that for regular momentum, where you have a conservation of energy step, a conservation of momentum step, and then a conservation of energy step. There, you should choose your system wisely for each phase of it, and it doesn't have to be the same for each phase. In this case, basically it was the same, but we didn't have to do it that way. You can choose differently for each phase.
How would we find the center of mass velocity for the 1D elastic collision again?
It's a good question. Let's just go ahead and do this one example. I want to remind you that the velocities can be greater than or less than 0, the way that we're defining them in this equation. So in the particular way I've drawn it, both velocities are positive. The velocity of the center of mass is the mass of one object times its velocity plus the mass of the second object times its velocity divided by the total mass. So it's literally a weighted average weighted by the mass of each object. And so, for example, the final velocity of object 2 would be twice m that velocity minus the initial velocity of object 2, which is what we're just calling little v. And you could simplify that further, but I'm not going to spend the time to do that. Okay. Continuing down our list. So I think we'd only gotten as far as impulse. So be ready to derive the general law of conservation of momentum starting from Newton's second and third laws. 1D elastic collisions, we just did an example. Center of mass frame, that's mostly important to understand what that term means. We use that idea to derive this equation, but I would probably not ask you explicitly to solve this problem in the center of mass frame or something like that. I might ask you find the velocity of the center of mass, which would be, yeah. 2D and 3D collisions where the masses stick together at the start or the end. So at the start, that means an explosion, or at the end, meaning where they hook together. Angular momentum, general law, including how it's changed by external torque.
Do we not need to, is the equipartition theorem and all the stuff on gases not going to be on the exam?
Oh, it is. That's further down. I left a little space here to write stuff. So, did you have a question about those things you want to talk about now?
Oh no, I thought that it was a very short list of
Okay. Okay. Definition of angular momentum as a vector in terms of omega and in terms of r cross p.
Professor, quick question going back.
Yeah.
I think we've done many examples with 2D collisions. For 3D collisions, is it the same idea where we would, instead of just X and Y, we would look at X, Y, and Z independently?
Yeah, exactly. Yeah. Okay. Differential equations. So remember, we only talked about differential equations literally for like 15 minutes. So I'm not going to ask you any hard questions about these, but I do expect you to understand what a differential equation is. Okay. Mass on spring and equivalent systems. Again, we didn't spend a lot of time on the time dependence of this. So prior to exam 2, we spent a lot of time talking about potential energy of a mass on a spring. So the main thing that you need to remember here is the equation for the angular frequency, omega equals square root of k over m, because we did use that earlier when we're talking about the molar heat capacity of a solid. And then the connection between the frequency, the angular frequency, and the period. Fluids.
Could you go over that? I'm sorry, the frequency, the angular frequency, and period.
Sure. So the angular frequency is 2 pi times the regular frequency, and that's 2 pi divided by the period, because the regular frequency is 1 over the period. For fluids, understand how the pressure, what the pressure is, and how it depends on depth. Fluid drag, we only talked about briefly, mostly in the context of terminal velocity. That's one important idea about it. So just be aware that when you're in the turbulent limit, the fluid drag is proportional to the square of the velocity. Instead of laminar flow, I should have written non-turbulent limit. And in that limit, the fluid drag is proportional. Sorry, in the turbulent limit, it's velocity squared. Non-turbulent limit, it's just velocity.
Is V a scalar value for F drag?
Yes.
Yeah.
Kinetic theory of gases, be ready to reproduce the argument of how this leads to the ideal gas law. The idea of absolute zero. The ideal gas law in the chemists and physicists versions.
Can we go over how the kinetic theory of gases relates to the ideal gas law, or do we just need to know the equation?
No, you need to be able to reproduce the derivation. So mostly, I think I'll refer you back to that class, but I'll kind of sketch it out for you. What we did, we had a box, and inside the box, we considered a cylindrical volume, and there were gas molecules that were moving within this volume. We said half the molecules are moving right. And we said then the average force exerted on the wall will be equal to the number of impacts times the delta P per impact divided by the time over which that occurs. And we said that the time is going to be the time it takes for all the molecules in this box to hit the wall. And so the one that's going to take the longest is the one that starts back here. So delta T was, I forget the symbol that we used for the thickness of this box, but let's call it D, would be D divided by the X velocity of that. So again, mostly I'll refer you back to that class, but you should be able to carry this through. And so we got from this to that P times V equals N times 2 times the average value of 1/2 mvx squared. And then, so this is the part that I want you to look up from that class. Then we use the equipartition theorem to say that the average value of 1/2 mvx squared equals 1/2 kBt. And so the factors of 2 cancel. And so that gives you PV equals N kBt, which is the physicist version. So let me just quickly look up which class that was in. This is class 29. Good question. Okay. Be ready to explain qualitatively for solid and quantitatively for gas why Cp is greater than Cv. Equipartition theorem, know about it, including the caveat about quantum level spacing. Be ready to use it to estimate the molar heat capacity of a specified gas or solid. Know that for a diatomic molecule, there are only 2 rotational degrees of freedom, and understand roughly why. Understand why for gases with more than one atom per molecule, the above predictions are only valid at high temperatures. Understand why for some solids, the heat capacity at room temperature is lower than at high temperature, and be ready to predict which solid has a higher room temperature heat capacity based on hardness or effective spring constant and atomic mass. Okay. Idea of latent heat. Terminal velocity. So we talked a little bit about that in the first section. Terminal velocity, again, is just when you're falling fast enough that your velocity is so big that the force of gravity downward is equal in magnitude to the force of air resistance upward. So let's say you might be asked to solve for what the terminal velocity is. You'd have to be told which regime are you in? Are you in the turbulent regime or the non-turbulent regime? So let's say if you're in the non-turbulent regime where the force of air resistance is proportional to the velocity minus BV. So you'd have to be given the value of that coefficient B, but then you could just say, okay, the magnitude of the air resistance force equals mg. So that means BV equals mg, and you could solve that for the terminal velocity. This should be V terminal. Random walk, be ready to reproduce the argument for a 1D random walk leading to an RMS displacement that's proportional to the square root of the number of steps.
Could you just go over the difference between RMS velocity and average, like average velocity?
Yeah, so there really isn't a difference, but let me try to clarify things. So we can talk about the RMS displacement. That's the main way in which we have used the term RMS. So X RMS is equal to the square root of the average of the square of the displacement. You could talk about a sort of average speed of diffusion, which you might define to be X RMS divided by the time that it takes to diffuse that far. So that would be like for the fume hood problem, you calculate an average speed of diffusion of about 1 centimeter per second, and that allowed you to figure out what minimum face velocity you wanted. I would not call this an RMS velocity though. So RMS velocity is actually not a term that we have used in this class. I did accidentally let through a usage of it, but I was aware it might confuse you. So I would rather you think about the term just average speed. But technically, when we use, but you might encounter it in other contexts. So the RMS velocity would be the square root of the average of the velocity squared. And actually, when you're using equipartition, you are calculating the RMS velocity, even though we didn't use that term, equipartition, because you're saying 1/2 mv squared on average is equal to 1/2 kBt. And so that's telling you that V on average is equal to the square root of kBt over m. Really, you're taking the average, the square root of an average of a square. So really, this is an RMS velocity, but we haven't used that terminology. So as far as we're concerned, average velocity and RMS velocity are the same thing. And maybe let's just use the term average speed of diffusion to talk about that other thing that's different, where this has to do with the net displacement from starting point to ending point, whereas this is the speed, this VRMS is the speed during one of those steps. Okay, combining error sources by adding in quadrature.
Can I quickly confirm that when you talk about kinetic energy of a particle, you're only talking about translational kinetic energy and not vibrational or rotational?
Yes. Yes, you know, so really the rotational and vibrational energies also have a kinetic component, and the translational energy is completely a kinetic component. But when we talk about the kinetic energy of a molecule, we ordinarily mean the translational kinetic energy. Okay, diffusion. So the equation for the RMS displacement in terms of the diffusion constant and time, meaning x RMS equals the square root of 2 dt, and d equals the mobility times kbt. So that second one, that's Einstein's diffusion equation, this equation here. And we made an argument that smaller objects have larger mobility, which means that their RMS displacement will be larger. Osmosis, the equation for osmotic pressure and the meaning of it. The energy needed for purification of water by reverse osmosis.
There are two equations for osmotic pressure, right? The density and the one with the density and the one with NVRT, or?
Yes, sort of. So we could write, so this is the one that's sort of more important, that the osmotic pressure is that. Just in general, if you have a height difference between two fluids for whatever reason, the pressure difference, delta P would be rho GH. So that's sort of different, but you know, let's say if you were asked to calculate what's the equilibrium height difference given a certain molarity, then yes, you would need both of those equations. I do hold you responsible for the 2 labs that we've done since exam 2. The first one was on momentum, and I think covered more or less the same ideas that we covered in class. Second one was on sound, and that really was different. Mostly a qualitative lab. So from that, I really do want you to qualitatively understand what Fourier analysis is. Very, very important idea in all fields of science. And also quantitatively understand the connection between wavelength, speed, and frequency for traveling waves, by which I mean that the velocity is the wavelength divided by the period, which you could also write as the wavelength times the frequency.
Could you go over what you mean when we have to understand a Fourier analysis quantitatively?
Mm-hmm. So let's say what I said was that I want you to understand that qualitatively. The quantitative thing is the connection between wavelength, speed, and frequency. Let's say if we're talking about sound and we're making a graph of the pressure minus the average atmospheric pressure as a function of time. And let's say maybe it's a purely sinusoidal variation. So this is roughly what you'd get if you were doing it for something that makes a very pure tone like a tuning fork. When we graph the corresponding Fourier amplitude, as a function of frequency, you would get a single peak. And the peak would be at a frequency f equals 1 over t, where t, capital T, is the period of the waveform. On the other hand, if you had a more complicated wave, so let's say pressure minus the atmospheric pressure versus time was some more complicated thing like this, but still repetitive. Whoops. So this is meant to be having this exact same wiggles over and over. So there's still some fundamental period, T like this, but there's additional structure. Then when you look at the Fourier amplitude as a function of frequency, you would still have a peak at the fundamental, which we could maybe call F naught equals 1 over T, but you'd also get peaks at integer multiples of that. So there'd be a peak at 2F naught, 3F naught, etc. And the relative height of those different peaks would depend on the details of the more complicated waveform. Good question. Other questions?
In regards to material being tested on from exam 1 and exam 2, are we more likely to be tested on something that we weren't tested on in the tests?
No.
Okay.
So to some extent the other way around, since the material that you were tested on in the previous tests is the most important material. So I'm likely to try to ask you a question about it again, just in a different way. But, you know, you should also be ready for questions that you weren't tested on before. So I have more or less finalized the exam. As usual, I need to do a little bit of tweaking on it just to make sure that it's really ready for prime time. It will be ready by 2:30 this afternoon. It will be either 3 or 3.5 hours in length with 2 10-minute breaks during it.
I have a question.
Yeah.
When will we get problem set 9 back? I mean 8, problem set 8 back.
Later today. So it has been graded. I just need to add up the grades. So if you're, you know, you could look at the version that I think you can look at your own version, yeah, even though it's still blind for us, and see the graders' comments. I just haven't added up the grades yet.
Okay, thank you.
And that reminds me, I will post the full solutions to that as soon as we're done here. I will also post the full solutions for exam 2, which I think I haven't gotten around to doing yet. The rewrites of your exam 2, those I'll grade as quickly as I can, but it might take me a few days. There's a lot going on right now. So, other questions? Okay.
Actually,
Go ahead, Davey.
I did have a question. If there's by any chance like an answer key to the sound lab or the other lab, I was wondering if like that could be like made available, because I think that, I don't know. I just didn't know if that was possible.
It's a good question. I think it's more, in terms of preparation for this exam, it's more relevant for the sound lab, because the momentum lab really covered the same ideas that we have gotten in the main one. So I will try to generate that. I'm confident that there is no such already existing key. Pretty confident. Let me check with Paul. But anyway, one way or another, we'll get something posted, let's say by noon tomorrow. So, it's a good idea. Other questions? All right, we did cover everything, all the questions that were talked about in the first review session, but I'm going to post the recordings of both of them. So if you want to watch that one, you can. All right, thank you.